Today's experiment showcases constant velocity motion. Newton's second law, or the momentum principle, says that the change in momentum is equal to the net forces on a system multiplied by the change in time. The net forces on the system is the total pushes and pulls on the system. To use Newton's second law to predict the future, we note that momentum is equal to the mass times the velocity. Therefore, with some algebraic manipulation, we can determine that the change in velocity over time is equal to the net forces on the system over the mass. In our experiment, since we are dealing with constant velocity, the change in velocity is zero. Therefore, the net forces on the system must be zero, as every object has some mass, but that mass is irrelevant, as any object of any mass would satisfy the equation. In my experiment, I used a golf ball with mass of 0.04593 kilograms. I set my coordinate axis with the positive x-axis as the floor of my kitchen pointing to the right, and the positive y-axis as the wall going up. I set up a tape measure against the wall to set my calibration stick at 2 inches or 0.0508 meters. I set the calibration stick closer to the beginning of the tape than the end of the tape due to the angle that the tape moves in due to the container that the tape resides. I then pushed the ball to get the system in motion and created the data points as shown in the table to extract the object's position. Using VPython, I adapted the code given to edit ball.m, which is the mass of the golf ball, to be equal to 0.04593. I also adapted the ball.pos variable, where the initial velocity of the ball in the x-coordinate is 0.105 meters. The y and z coordinates of this vector remain 0 as the ball has no initial position in the y or z direction. Ball.vel was also adapted for this observation, where the initial velocity of the ball is 0.7576 meters per second. I determined the initial velocity by taking the first 2 data points in my observation. Since I started my observation after the initial push, the initial velocity observed should be a decent approximation of the initial velocity. The initial velocity is the change in x over the change in t over those data points. So the change in x is 0.025 meters and the change in t is 0.033 seconds. So the initial velocity is 0.7576 meters per second. I also changed delta t to 0.033 seconds based on my observation and set the t parameter of the while loop that calculates the motion prediction and visualization to 0.834, which was the last time the observation was set. If we run the module, we see that the model moves in the positive x direction just like it did in the observation, and that in the graph, though the initial points don't start at 0, 0 based on our initial position, initial time not being 0, it does move in a positive linear direction such that constant velocity would be equal to 0. Taking the data points from the model and comparing them to our observation in Google Drive, we see that our observation and model diverge over time. I would assume that I chose a starting point of my observation too soon after the initial push, and the initial velocity was faster than what the constant velocity would have been a little bit later if I chose a different starting point. So the golf ball was probably not traveling yet at a constant velocity when I calculated the initial velocity. Nevertheless, both graphs are relatively linear and show a somewhat constant velocity. If we changed our choice of orientation of the axis such that the positive x-axis now follows the wall up and the positive y points to the left on the kitchen floor instead of to the right, our ball would have moved in the negative y direction, so that the graph would have pointed down and to the right since it would have traveled in the positive x direction but the negative y direction. Now, is it possible for me to say how many pushes and pulls were added together to give a zero net force in this case? I would say in this observation, possibly. The only push would have been my finger pushing the golf ball to the right, and then any other pushes or pulls would have negated that to be a constant velocity. However, generally, I don't believe this to be the case. If the object is moving at constant velocity, we may not know how many pushes or pulls there are, but it really doesn't matter. As long as the net force is equal to 0, we would know that the constant velocity would be equal to 0.